insights you need to be, well, properly informed without getting totally buried in information.
Think of us as guides, maybe, cutting through all that noise to get to what really matters.
And today, wow, we are diving deep into something that's, it's fundamentally changed things, how we live, how we work, how we interact. We're talking about the future of hybrid work models.
That's right. And we've sifted through a really fascinating collection of your sources on this. We've got tech industry reports, HR strategy guides.
Analyses from real estate firms, which is
Oh
interesting.
yeah, and behavioral psychology studies, tons of employee surveys. It's a properly rich data set we've got to work with here.
Absolutely. So, our goal today is to really unpack where hybrid work is right now and where it seems to be heading. We want to get past the buzzwords,
Hmm.
and explore what it actually means
Hmm.
for productivity, for company culture, for leadership,
Hmm.
even for the whole point of having an office anymore.
Yeah, we'll look at the different models popping up, those often surprising findings on productivity you mentioned, and also the pretty significant challenges. I mean, companies and individuals are really navigating some tricky stuff here.
Right. And we also need to touch on technology's role, how leadership has to adapt.
And then maybe zoom out a bit, look at the bigger picture, the broader societal impacts of this huge shift.
I think even if you feel like you know hybrid work,
Hmm.
I guarantee some of the things we found in these sources will make you think again.
Definitely. There are some fascinating twists in there.
Okay, so let's unpack it. We all hear hybrid work constantly. What does it actually look like in practice? It's clearly not just, some days in, some days out,
No, exactly. That's one of the first things we had to sort of clarify from the earlier reports in your stack. That simple definition just doesn't cut it anymore.
right?
The more recent analyses, the deeper dives in your sources, they paint a much more nuanced picture. We're seeing a whole spectrum.
Like what specifically?
Well, you've got office centric models where being remote is really the exception, not the rule. Then there are flex hybrid setups where maybe teams get to decide their own rhythm, their own schedules.
Okay, that sounds more autonomous.
It can be. And then you even see things like hub and spoke models emerging. So instead of one giant headquarters, companies might use smaller distributed satellite offices.
Interesting. So less reliance on a single central location.
Exactly. The main takeaway here, I think, is that companies are actively experimenting. They're trying things out. There isn't, one single playbook everyone's following. Not yet, anyway.
And what's behind all this experimentation? I mean, it feels like it exploded pretty quickly. It didn't just materialize out of nowhere.
No, definitely not. Your sources point to a few key factors converging really powerfully.
Okay.
The biggest driver, I mean, hands down, is employee demand. You look at survey after survey across so many industries, and there's just this incredibly strong preference for flexibility.
People got a taste of it, right?
They did. They experienced the upsides of remote work, cutting out the commute, having more say over their day, and often, yeah, a better work life balance, whatever that means for them. And frankly, they're just not willing to give all of that up.
Makes sense. What else?
Well, technology enablement was obviously huge. You couldn't have done this, not at this scale, without really solid video conferencing, cloud platforms for collaboration, good project management tools. That infrastructure had to be there.
True. The tech had to catch up, or rather, we had to catch up with using it effectively.
Yeah, right. And then let's be honest, there's the appeal of cost savings for companies, particularly around real estate. Reducing that office footprint can mean serious savings. One report we looked at projected potential savings in the tens of millions for big corporations just by optimizing their office space.
Wow. Okay.
Yeah,
Tens of millions. That's definitely a motivator.
it certainly gets attention in the boardroom.
Okay. So employee demand, tech enablement, cost savings. That makes a lot of sense. But let's get to the really big question everyone keeps asking.
Definitely challenges.
One that kept popping up in the sources is this idea of proximity bias. The feeling or maybe the reality of interactions that build team spirit.
So you can see that we already solved, let's say, game degree from equation using Ezouidi Theorem. You see the exact symbol of the following groups are expressed in terms of complex exponentials, which is a direct outcome of the recursive steps you have to know. As you can see, Ezouidi Theorem does not rely on numerical approximations. The roots you have derived here are exact, not subject to the error-prone calculations that come with numerical methods. This approach ensures that you can find the roots exactly even for high degree polynomials that are too complex for classical methods to handle the exact roots. But Ezouidi theorem doesn't. The roots here are derived recursively, where we solve for them step by step. This formula breaks down the polynomial into manageable components, allowing us to derive exact sample values instead of approximations. Let's see how this works in practice. Notice here, because of the recursive structure, this Ezouidi theorem, we were able to derive these roots systematically and precisely without approximations. This is the point to the power 18 that we are going to show for you. Okay, this is our point to the power 18. This one you can see. This is x to the power 18 minus 18 x to the power 17 plus 153 x to the power 16 minus 116 x to the power 15 plus 3060 x to the power 14 minus 8568 x to the power 15 plus 18,546 x to the power 12 minus 31,924 x raised to the power 11 plus 23,758 x to the power 10 minus x to the power 9 minus 50 okay, minus 393,813 x to the power 8 plus 1,718,460 x to the power 7 minus 4,065,433 x to the power 6 plus 6,172,446 x to the power 5 minus 6,122,954 x to the power 2 plus 4,083,180 x to the power 3 minus 1,750,131 x squared plus 437,553 x minus root of 101. Okay, so here you see this point to the power 18. In fact, it's not easy to solve it, but we banish all the new coefficients after the new 18th degree from the equation that relates to the original 18th degree from the equation, and all the sk minus 1 vanish except s8 and s17. Okay, and we will obtain a quadratic equation. This is the new idea, a new process, approach. We can, let's say, write as a quadratic equation or a cube equation or quartic equation or a septic equation whatsoever. Okay, this is the tools of the Ezouidi theorem works here. Okay, now I'm going to show you the roots, the exact sample roots of this degree formal equation. We obtain, let's say, S0 equal S1 equal S2 equal S3, S4, S5, S7 equal also S10 and S11 and S9, S12, 13, 14, 15. All of these new coefficients of the new 18 degree form equation vanish and tends to zero, except two symbolic values which are S8 and S17, which are different. These values are separate. Okay, meaning there is no approximation. There is no, for example, can be written as 4868 to 18.19998 so on, etc. Here it's a symbolic value. Okay, so in line condition method, which often use numerical approximations, the theorem provides precise sample solution. This ensures that the roots we obtain here are exact and not subject to the errors that arise with numerical methods. Once we have the sample coefficients, we should use them to find the exact roots of this 18th degree form equation. And this is, in fact, can stack you. We never find this kind of sample roots without using the Ezouidi theorem. For this equation, we obtain x to the power 18 minus s0 to the r x to the power 17 plus s1 to the r x to the power 16 up to s17. Here you can see this equation needs as to simplified form of 4x to the power 18 minus s8 all the rx to the power 9 plus s17 equals 0. So the fact this is the quadratic equation when setting y equal x to the power 9. And the rest work is gonna be the decimal formula that we're going to use here. The decimal has to be labeled as S1 of order R dash, which is equal to negative S8 of order R all squared plus 4 times S17. Okay, now I'm going to calculate the value of this S1 of R, and then we are going to derive all the possible exact roots of this degree from the equation. So this is the value of x9, which is equal to this. Okay, you can see 18 raised to the power 18, all raised to the power half. So it will be 18 raised to the power 9 is the common factor. I'm going to put outside. Okay. After that, finding the ninth x roots of this new 18 degree from the equation, why we call the ninth x first ninth x root of this 18 degree from equation, because the equation, the 18 degree from equation had been simplified to a quadratic equation. Okay. And we suppose that y equal x to the power 9. We are going to solve for y, then go back to find the ninth root of this value that we find. Here you can see sigma. Sigma denotes the exact roots. Xk denotes the x roots. Meaning there is a relationship between the x roots of the new 18 degree from equation and the exact sample roots of this 18 degree from equation, which that will start. Now after simplifying, we can, let's say, focus on the last 18th exact roots. This 18 degree from equation, which is equal to 1y1 because 18 over 18. Then you can see the next value of the next term. Here we have 18, and down the denominator is 18, so it has to be cancelled. So that's why here it's written 1. 18 over 1 is 1, or 18 over 18 is 1. So 1 plus negative 48,619 plus the square root of 236 billion, 3,000,000 and 600,689 plus root of 101. All divided by 2 raised to the power 1 over 9 times exponential 2ki 5 over 9. So here you can see the roots are expressed in radical and exponential form. And Abel theorem says that there is no general formula to find or derive the nth root, the nth exact root of any integer form equation, especially. And here in this example, you can see that we derived all the 18 roots with radical and exponential form. So this theorem bypass Abel's theorem, and also you can see that this is the exact sample roots of this polynomial. The roots here are expressed in terms of exponential and radical, which are direct outcome of the first step below. As you can see, Ezouidi theorem does not rely on numerical approximations. The roots we have derived are exactly not subject to the root problem. So now what's advised is to apply Ezouidi theorem and try to work with this 18 degree from equation and find out the exact sample roots. Okay? And in this method, we will never use approximation method or guesswork. Here we give exact sample roots. Thank you for listening and see you next lecture. Goodbye.